have. And then what do I mean by symmetric? It means the norm is invariant under permutations of coordinates. So you can rearrange the ordering of the vectors, like you can shuffle the coordinates of this vector x, but its norm won't change. So that's what I mean by a symmetric. So that's the assumption we have. And what is the goal in this model is to find an oblivious solution S that minimizes the expected F norm of the random cost vector. Okay, what do I mean by oblivious? It's like, given information like all this distributional information, you fix a solution S, then that leads to a random vector Y, right? You haven't yet seen the realizations. Then the quality of the solution is measured by looking at, I don't know what, does anyone know how to? Anyway, it's okay. Right. So the quality of a solution S is measured by computing the expected F norm of the induced cost vector. Okay. Is the problem statement clear? You fix a solution, its quality is measured by like going through all possible realizations according to the distribution and looking at like whatever are the random cost vectors that get realized and looking at the expected norm of this random. Okay, so the expectation is over the randomness in these input cost variables. Now let's look at two concrete models of this problem. So the first one comes from load balancing. What do we have here? We have a set of n independent jobs, which are stochastic, and we have m unrelated parallel machines. So for we are given random variables xij, where xij denotes the random processing time of job j on machine I. We are going to assume that xij and xi prime j prime are independent whenever j is not equal to j prime, which means the xij variables can have correlations for the same job. If you look at two different machines, the processing time variables can have correlations. But if you are looking at two different jobs, then there should be independence between them. And we are also given a monotone symmetric number. Now what happens, like when you assign these jobs to machines, so each job goes on exactly one machine. For instance, I've drawn an assignment here. We have 8 jobs and 4 machines, and I put jobs 2, 3 on machine 1. So what is the load on the first machine? It's simply x12 plus x13, because that's the processing time of job 2 on machine 1, and this is the processing time of job 3 on machine 1. Similarly, you do this for all other jobs and basically all other machines. So that's your random cost vector. So it's a random m-dimensional load vector. And the goal is to find an assignment of jobs to machines that minimizes the expected S norm of the load vector. Any questions so far? Let's consider another problem, which comes from spanning tree applications. Here we have an undirected graph G on n vertices. Each edge in this graph has a non-negative stochastic weight. Okay, so I'll denote that by XC, and we'll assume that these edge weight variables are independent. So each edge has its own like independent random variable. And we are given a monotone symmetric norm of dimension n-1, because we are going to be working with spanning trees. So feasible solutions to this problem are given by spanning trees of the graph. So for instance, if the graph is drawn in black and I have highlighted a spanning tree in this graph, the cost vector that is induced by the spanning tree is simply you have n-1 entries, and for each coordinate, like we have the variable corresponding to one of the edges. That's all. And like observe that the ordering does not matter because we will be working with the symmetric now, so it won't matter. So now the goal is to find a spanning tree T consisting of edges E1 through En-1, such that the expected F norm of the spanning tree cost vector is minimized. Okay, so this is the second problem. So these are the two concrete problems that you should have on your mind when thinking about stochastic min-norm optimization. So of course, you can like ask this question for many other settings, but these are the two problems that we studied in my thesis. Okay. Right. So let me also state some, make some remarks and also state some. So in the general framework, like in the general problem, we are trying to find an oblivious solution S that minimizes the expected F norm of the induced cost. Observe that there are like three sources of complexity here. Okay. First one comes from, like, we have an underlying combinatorial optimization problem. So we have some constraints that come from this combinatorial optimization problem, and we want to be feasible in that. So we are only allowed to like, so the solution should come, it should make sense for the combinatorial optimization. So that's, as we have seen, like that is usually like it leads to like a non-trivial problem in it. Then the second source of complexity comes from stochasticity of cost. Like now we have like random cost. We have to work with distributions. And the third source of complexity comes from controlling the norm of the cost vector. So usually like we study like the sum of cost vector entries or the maximum of cost vector entries. Right? Like and we study like many such special cases in combinatorial optimization problems. But what if we are looking at like an arbitrary monotone symmetric norm? So that can also be like a bit like difficult to work. And so this adds another layer of complexity. So in this stochastic min-norm optimization, like we are trying to control all of these three complexities at the same time. We'll make some assumptions in this model. So first of all, we'll assume that complete distributional information about these random variables is given to us. So whatever is the, let's say in load balancing applications, the job size random variables xij. Let's just say you're given the entire distribution. It could be like a list saying, oh, this job takes size 5 with this probability, size 10 with this probability, and size 0 with this probability, and so on. Because the idea is that we don't want to worry too much about like how the input is given to us, that we can just, we have the entire list, like, but how do you work with this now? Like, how do you design approximation algorithms? That's the goal here. And we'll also assume that if we wanted, we can sample from these distributions. We can get an independent sample from these distributions. We'll also assume that like we can compute some simple functions of these distributions, like expected value. If you want to evaluate its moment generating function at some value, you can do that. If you wanted to like truncate the random variable at some threshold, like basically like you have some input random variable and you say, oh, I want to cap its support at like some value 5, then you can do that operation, say. Or like you want to say anything that's below 5, I want to zero it out, and anything that's larger than 5, I want to retain it. Okay? So you can do all these simple operations. We'll just assume that you have a lot of power, computational power to compute these functions. Okay, and also if you wanted to, given a fixed solution, you know how to compute, how to have access to the random vector ys, and then you can use some sampling procedures to estimate this expected. So let's just say you can do all of this, but how do you even like get a good candidate solution? That's the question. What is the significance of our work? Like, why are we studying such general models? First of all, like this reading group is on stochastic optimization. You have already seen like many talks, and so uncertainty is like present in many real world optimization problems. We should have tools to optimize against it. And then like working with such a general model, like the idea is that like it's useful to have a principled approach that works across multiple settings that arise in combinatorial optimizations. We are trying to like unify. So working at the generality of monotone symmetric norms has several benefits. Let me mention 3. Right? So first of all, like many popular objective functions, such as minimizing the sum of costs, of the cost vector entries or minimizing the maximum cost vector entry, these are monotone symmetric norms. The max norm and the sum norm, these are monotone symmetric. In fact, even LP norms are also monotone symmetric. Many a times people interpolate between the sum and the maximum and the sum by using, like, say, L2 norm or L3 norm, or like in general an LP norm. LP norms are also monotone. There's yet another class of monotone symmetric norms called as topple norms. What is a topple norm? It's simply the sum of L largest entries of X. Okay? So if you have a vector, look at the L largest entries and sum these numbers. That's the topple norm of this vector X. Observe that when L is 1, you recover the max norm, and when L equals the dimension of the vector, then you recover the sum norm. Okay, so topple norms are another way of interpolating between the max objective and the sum objective. Yeah, so you can fine tune whether you want to take a egalitarian view or a utilitarian view. So there is an added level of flexibility that you can get. Right. So if you're working at the generality of monotone symmetric norms, then we are actually unifying algorithm design principles for a wide class of objectives under one umbrella, which also contains like popular objectives. So we are not like losing any standard functions. We're generalizing. Let me mention another interesting benefit that we get by working at the generality of monotone symmetric norms. So this comes from like the closure properties of the class of monotone symmetric norms. So let's say if you have two monotone symmetric norms, F and F prime, then if you take a non-negative linear combination of these two norms, alpha F plus beta F prime, then even this is this norm is also this is also a monotone symmetric norm. Okay, so what do I mean by this? Alpha F plus beta F prime of X is simply defined as alpha times F of X beta times. So it's defined pointwise in this way, and this is also a monotone symmetric norm. You can verify all the axioms. Okay? And another interesting closure property is under pointwise maximums. So if you have two monotone symmetric norms F and F prime, then the maximum, the pointwise maximum, is also a monotone symmetric norm. If I were to look at the max is defined. Never mind. I won't write this one explicitly. It's just like pointwise maximum of all these of F of X and F prime X. That is also monotone symmetric norm. So how is this useful to us? Let's say if you are trying to solve a feasibility problem, I want you to find some solution X in some set P, say. And I want you to find a solution X that satisfies the following budget constraints. Okay, so I want the first norm of X is at most some given budget B1, and I want some other norm of X to be at most B2, and then a third norm of X to be at most B3. So something like I want something like the first norm of X, that there is some norm 1. I want this to be at most this, and then simultaneously I want some other norm to be bounded by this, like the L1 norm should be at most this much. The L infinity norm should be at most some quantity. L2 norm should be something else, but like we have multiple such budgets. If you had a feasibility problem like this, then we can simply reduce it to a norm minimization problem with a single norm. What do? You just define a function g of x, which is just the maximum over the scaled norms, where you scale each norm by the given budget. So if you do this, then you get a monotone symmetric norm. You can show this. So which means you're solving a single norm minimization problem and automatically satisfying a bunch of budget constraints. This is kind of cool, right? Like, so if you can, if you have like a general model for handling monotone symmetric norms, then you you can do like many interesting combinations. Okay.
You need like
Any
gx
questions?
less than equal to 1 or something.
Yes, yes. So the feasible solution exists if and only if the norm minimization problem produces a solution with objective
Oh,
extension,
okay.
right?
Okay,
Yeah,
okay.
good
Yeah,
question.
yeah,
Like,
okay.
so a feasibility problem is alpha satisfiable if I can find a solution to the norm minimization problem with objective at most alpha. That's where all of this is leading to. Okay. Okay. So what are our contributions in this work? Our main contribution is that we give a framework for designing approximation algorithms for stochastic min-norm optimization. So what does this framework have? It has like two main components. The first component says that the first component lets you work with simpler norms. So let's start with the problem. What's our objective in stochastic min-norm optimization? We're saying find me a solution S such that like it is within some order alpha factor of whatever is the expected norm of an optimal solution S star. Okay, so that's what we were trying to do in the beginning. So what this first component says is that, okay, like this norm F can be a very complicated object. Let's move to something more simple. So what are these simpler things? We'll say that we are going to give a reduction which loses a constant factor, and then we'll move to something with top L norms. Okay, so top L norms are like intuitively easier to picture, right? Like, so an arbitrary monotone symmetric norm can be complex, but top L norms are easier. It's more like, oh, it is the sum of the L largest entries. So what we say is this problem reduces to this problem. And what is this problem? It says, give me a solution S such that the expected top L norm of this solution vector, is within an order alpha of the expected top L norm of this fixed optimal solution. Okay, and I want you to do this for all L's that are powers of 2. Okay, so there are like log m many powers of 2, and you just need to do this. Observe that I'm not asking for a simultaneous optimization of all top L norms. Now, what I'm saying is you start with an original problem. For this F norm optimization problem, there is some optimal solution S star. Let's just say I told you what this, or let's just say you were able to somehow guess the expected top L norm of this optimal solution for all powers of 2L. Okay, so let's say if you somehow knew the answer to this, which you'll do by guessing, this is like a standard thing to do in optimization. But let's just say if you knew these quantities, I'm asking you to solve a simultaneous budgeted optimization problem where I want you to pick one common solution is such that the expected top L norms are within the budgets that you were prescribed. Okay, so it can be that the optimal solution for this top L objective could be much smaller than this thing. I'm not worried about that. Okay, I just want you to stay within the budget afforded by the optimal solution. So that's the first component. You work with simpler norms. The second component is basically saying, how do we reason about the expected top L norm optimization problem for a single top L norm? Okay, so this one is something like a simultaneous budgeted optimization problem for log m many norms. Okay, but how do you solve this problem for a single top L norm? So that's our second component. Like, so how do we do this? And observe that like this is not in itself like a easy problem to do, because how do you control the expected top L norm? It's like you have a random vector. For each realization of the random vector, there are some L largest entries, right? So there is no such fixed guarantee that always the first L coordinates will be the largest one. So depending on the realization, like there is some set of L largest things and you're looking at them. So in some sense, like all the coordinates are contributing to the top L norm, expected top L norm in a very complex way, in a very like non-separable way. Okay? So we'll come to this later, but this in itself is like a non-trivial problem. And we give some tools for doing it. Any questions so far, like regarding like this framework? Okay. Now, and what do we do? Like, so we design this framework and we then apply this framework to obtain approximation algorithms for stochastic min-norm load balancing and stochastic min-norm spanning trees. Okay. And I'll just take like the main results, all the approximation guarantees towards the end of the talk. I don't want to focus on like how exactly we obtain these. Maybe for like, if we have time, I'll mention a bit about stochastic min-norm spanning tree, how we solve this. But for load balancing, I'll only be mentioning like what results we get. And all of this work, whatever I'm going to present today, it has mostly appeared at 3 conferences, FOX 2020, ICALP 2021, and SOSA 2022. And you can also find like detailed proofs in my thesis. Okay, so now let's get into some discussing some main proof techniques. Like, so how do we why does the framework work? Like, what ideas went into the framework? Okay? So how do we reason about the expected F norm of a random vector, where F is an arbitrary monotone symmetric norm and Y is a arbitrary product distribution? So the only information we have is that the coordinates of yi have independence between them and the coordinates are non-negative. That's the only information. And then for F, we are told that it's an arbitrary monotone symmetry. Okay. So the first component of the framework was a reduction to simpler norms. Let's see, like, what can we do here? So it's a classical result from majorization theory. It's more than 100 years old, like roughly, I think in 1920s, maybe. Hardy, Littlewood, and Follier studied monotone symmetric norms. And what they showed is that if you have some 2 non-negative vectors x and y, and if it holds true that the sum of L largest entries of x is dominated by the L largest entries of y, and this happens for all L's. So the first entry of x is dominated by first entry of y, and then the sum of the first 2 entries of x is dominated by the sum of the first 2 entries of y, and so on up to the top m entries. Then for any monotone symmetric norm f, the F norm of x is bounded by the F norm of y. So if you ensure this, then you get this for all monotone symmetric norms simultaneously. So in some sense, like top k now should be viewed as like a basis, where if you can get some property for this, then it just automatically implies the property for all monotones. And this formed this was like the basis of Chakrabarty and Swamy's framework for the deterministic version of minimum norm optimization. And this is the problem that we generalized to the stochastic setting. And that's what like started our work. So an actual question to ask is, does this property extend to the stochastic setting? Something like if I were to introduce some expectations here, then does it imply something like this? Okay, that's the question. In an approximate sense, yes. Okay, so what do we show? If you have 2 product distributions, y and w, and if you are told that the expected F norm, the expected top L norm of y is bounded by the expected top L norm of w within some factor alpha, and this holds for all L from 1 through n, then the expected F norm of y is within an order alpha times of the expected F norm of W, and this holds for like all monotone symmetric norms simultaneously. Okay. Any questions so far, like regarding this statement? So of approximate
of alpha in this case.
Yeah, what does alpha depend on?
Oh, it's just some factor. Like, so for any real number, like, so basically, like, one of the properties of a norm is that like they're homogeneous, right? So if you scale all the entries by lambda, then your norm scales by absolute value of lambda.
The implicit
So,
constant there is it small?
oh yeah, you'll be, W should be seen as the optimal solution here, optimal solutions vector. Ignore like alpha, like for now, just think of alpha as one. It doesn't matter. Like, so usually like this alpha can be taken inside. You can scale all the entries of W.
The implicit constant in big O of alpha, how big is it?
Oh, okay, yeah. So this big O is like say 7.638, like something under 8. Okay, so I lose an additional factor 8. Yeah. Okay. Anyway, so the proofs that I'll be talking about, like I'll be very, very like loose with the constraints. I'll just like incur like a lot of losses. I won't really care. Like the idea is that like how do we come within constant factors or something like that will be the. But anyway, so yeah.
Does the constant depend on the distributions or only on alpha?
No, it doesn't depend on alpha. It doesn't depend on the distributions. This is like a universal theorem. So as long as these are product distributions, and this is a monotone symmetric norm. So if you like forget this alpha for now, because oh, by the way, the reason I'm saying forget the alpha is okay. I need to edit. Okay, the reason I'm saying like we can forget alpha is because f of lambda x is lambda f of x for norms. Right? So it's like ignore the alpha, like alpha is not doing anything here. It will just show up directly. The main point is that if expected topple norms of y are bounded by the expected topple norms of w for all else, then the expected f norm of y is within 8 times the expected f norm of w. That is all. Like that, and it's universal. You get this property, then you automatically get this property for all monotone symmetry. Right? Okay. And the 8 can be, maybe it can be improved for like some special assumptions on y and w. But this statement holds for all non-negative product distributions y and w. Yeah, it's an absolute constant. The reason I introduced alpha is because let's say there was some hidden optimal solution that you're trying to approximate. Then you get some with alpha equal to log m or something like that. Like you were able to show this condition, then you have obtained a log m approximation. That's all I meant. Like it's not really playing any. Another remark that I want to make here is that like we can incur a further factor to loss and just like work with L's that are powers of 2. Why is this? This is simply because observe that top 10 of X is at most 2 times top 5 of X. Right? Because the sum of 10 largest entries is within like a factor 2 of the sum of 5 largest entries of X. So if you want to really like control the expected topple norm, just do it for like powers of 2, lose another factor 2. It's okay. It doesn't matter. Like all constants are like the same for us for now. Okay. So this will be important because whenever you're trying to solve like an optimization problem, like simultaneous optimization problem, you want to minimize the number of problems that you're solving simultaneously. It just helps to have like a sparser collection of things that you're trying to control. Okay, so we'll try to control the expected topple norms only for powers of 2. Okay, cool. Yeah, please interrupt me if you have any questions, because as we move forward in the talk, like things can get a little bit more complicated. It helps to, yeah, I would appreciate if I don't lose my audience. Okay, now, so why does approximate stochastic majorization hold, right? Like again, why can you just go from, like going from top L norms to F norms was easy, like more like it was given by this classical mathematical result. Why can you also generalize this to expected top L norms and expected F norms in the stochastic setting? So this is actually like a consequence of a more fundamental theorem in some sense, where what we show is if you're working with the expected F norm of a random vector Y, then actually I can, it suffices to, like, so there is another quantity, I'll define this shortly now. I'm saying this expected F norm of Y is within a constant factor, both upper and lower bound wise, from this number, which is the expected F norm of Y sorted in the decreasing order. Okay, so what do I mean by this? Yeah, so Y with downwards arrow means Y sorted in decreasing order. Okay, does that make sense? Like, so take a realization of Y. So each component is sampled separately. And then whatever realization you get, sort it in decreasing order. So the first coordinate is the largest, second is the second largest, and so on. Okay. Then, so each realization gives you a different ordering. But in all these orderings, the first one will always be the largest, second will be the second largest, and so on. I'm saying, like, look at this little y vector, which is the expected value of the sorted y vector. Okay. So what I mean by this is the LH entry of this vector is simply the expected LH maximum of the random vector Y. Does that make sense? Okay. And also observe that the expected top L norm, the sum of the L largest entries of Y, if you were to look at the expected value, then it is simply the top L norm of this little y vector. Okay. Now, what this theorem, this main theorem is saying is the expected F norm of Y is within a constant factor. It's theta, not just like big O. It's theta of the F norm of the expected sorted vector. Yeah. You cannot just
in the theorem.
So this
you assume that F is symmetric, sure.
What?
Do you assume that F is symmetric in the theorem, or?
Yeah, F is monotone symmetric. Yes, F throughout the talk it will be a monotone symmetric norm. Okay, so you couldn't have said something like this. You cannot just say exchange the expectation and the norm just in a trivial way. Like you cannot do this, right? Why? Because like Jensen's inequality can lead to a huge loss. Let me give a quick example. So let's say if you consider like the random vector Y, where each coordinate is a Bernoulli variable, it activates to size 1 with probability exactly 1 over n. Okay, so let me, oops. Oh, sure, like I can use this. So Y I takes size 1 with probability 1 over n and size 0 otherwise, then the expected maximum of yi is like roughly 1 minus 1 over e. Okay, in expectation, with probability 1 minus 1 over e, one of the coordinates activates, right? You have m coordinates and you have like m Bernoullis. So 1 minus 1 over e of the times, one of the yi is activate. So the maximum, expected maximum is roughly 1 minus 1 over e. But if you look at the max of the expected value of the yi's, then this is just 1 over n. The expected value of each coordinate is a small quantity. So if you were to just like exchange the norm and the expectation operator, you lose a lot. But what this theorem is saying is that if you were to sort your random vector and then apply the swap, you exchange the norm and the expectation operator, you only lose a constant factor. Okay, so think of it as like some sort of like going halfway through Jensen's inequality, like a midway Jensen's inequality. You do some modification before applying Jensen's. Okay. Any questions regarding this? So why does approximate stochastic majorization follow from this? It's simply because you know that the expected f of y can be compared directly with the f norm of the sorted y vector. So instead of like working with y and w now, like this is simply saying the topple norm of the expected sorted y vector is within an alpha factor of the topple norm of the expected sorted w vector, and then the deterministic version of majorization inequality takes over. So that's why like it is just a consequence. So this is a more fundamental result than approximate.
Sorry, Sharat, I'm not quite understanding.
Yeah.
So if your norm is symmetric though, why do you need to resort your vector? Why are you sorting it in decreasing order if it's symmetric?
Oh, I want like larger coordinates to accumulate at the top. Because if I don't, like for instance, if I don't sort, then the expected size in each coordinate is just 1 over n. Okay, so consider this case where the random vector only coordinates. Each coordinate is activating with probability just 1 over n. So if I look at the expected size of any coordinate, it's just 1 over n. So the maximum is only 1 over n. But if I were to look at the expected maximum coordinate, it's a constant. Okay, so why is there such a huge gap? It's because even though each coordinate is activating with a very small probability, which leads to like a small number, but the maximum of the coordinates is actually quite large. What we are saying is like, if you were to just like sort the vector, then the larger quantities will come at the top. And for a norm, larger quantities make more impact than smaller quantities. And you want to accumulate them. You don't want to like diverse, like lose the power of the norm just because like it was spread out. Think of it that way. Like, so if you are working with like the L2 norm or something like that, like, so if one of your coordinates is n, then you know that your norm is like n, right? But if you were to split this n across n coordinates, each of just size 1, then your L2 norm will be like square root n, right? So you lost your norm's power by like distributing the values. So norms are usually large, like so given the same budget on the sum of the entries, the best way to maximize your norm is to accumulate all of them in a single coordinate and then like do this. But that's like a different optimization problem. But what's happening here is that like sorting basically ensures that the first coordinate keeps collecting like the largest instantiation for each largest entry for each instantiation. And that is what like any other questions, like this is like the most important theorem in my thesis. So it makes, I'm happy to spend as much time as needed to explain like its significance. Okay. Okay, cool. So approximate stochastic majorization holds because of something more fundamental. It's this result. The expectation and the norm can be exchanged as long as you sort the random vector before applying the swap. Okay? And the lower bound here is simply because of convexity. Norms are convex. So just another quick remark. So if you are working with expected f of y, f is a symmetric norm. First of all, there is equality when you do this. So you can sort without losing anything. This is equality. And then now you apply Jensen's inequality. Norms are convex, so you get like expected. The lower bound argument is easy, just follows from convexity and symmetry. But the upper bound argument is where like you have to do something non-trivial. Okay. Now, so why does this result hold? Okay. Let's look at this. Now I want to convince you in the next like 5 minutes or something that the expected F norm of Y is within a constant factor of the F norm of the expected sorted vector. So here's a very like high level proof sketch. Okay. I'll consider this integer random variable, which I'll call n greater than theta of Y. So it counts the number of coordinates of Y that are greater than theta. So it's parameterized by theta. So for each theta, look at the number of coordinates of Y that are larger than theta. Okay. And so as theta increases, this number goes. So it starts when theta is 0, this random variable is like m always, because your random variables are non-negative, right? So let's just say it's around m. And then as theta goes to infinity, then this random variable goes to 0. But this is also like a random variable because depending on the realization of phi, this quantity keeps changing. So another way of writing this theta of Y is simply the summation over I, the indicator vector that yi is greater than theta. Does this make sense? Like if I'm just counting the number of coordinates greater than theta, then let's simply look at each coordinate and just have an indicator variable which says, is it greater than theta? So that is all this n variable is doing. Okay. Now I'm going to plot the expected value of this random variable against theta. Okay, so what am I doing? This expected histogram curve is saying for each value of theta going from 0 to infinity, I'm going to look at the expected value of this random variable. Okay, so what is the expected value of this random variable? It's simply the sum of probabilities that the coordinate yi exceeds theta. Yeah, what is this? It is simply the upper cumulative distribution function, right? And I'm just like summing that across all coordinates. That is all. Like so the expected histogram curve says, take the upper cumulative distribution function for each coordinate and just sum those up. So it starts from m and goes up to 0 as theta goes to infinity. That is all. That's the blue curve. Does that make sense? Okay. Next, I'm gonna define something called a threshold tau L. Okay, so what is tau L? It basically says the point, the theta value for which the height of this blue curve is L. That is all. That's tau L. Okay. And tau 1 is basically the point where the height of the curve is 1. So in some sense, it's a proxy for the Lth maximum. Okay, so what is this expected value saying? It is the sum of probabilities that yi exceeds theta, right? So let's say if theta is tau 1, I'm saying the sum of probabilities of the coordinates exceeding tau 1 is 1, which means, roughly speaking, probabilistically speaking, tau L is the point where in expectation, I expect to see one coordinate crossing this threshold. Does that make sense? Okay. Okay, so tau L is the coordinate, is the threshold where in expectation, I expect to see L coordinates above tau L. This can be rigorized too. Like we can show that like tau L is actually bounded by the expected value of the Lth maximum. Okay, but let's not get into that. But it's just like roughly like tau L's are where. So this blue curve is basically the sum of upper cumulative distribution functions of the coordinates, And so from this blue curve, you can draw this, like, because you recall that, like, you're given the distributions of the yi's. You know how to draw these cumulative distribution functions. Just sum those, and then look at like the points where the height is exactly like 1, 2, 3, and so on. Okay, so you have a bunch of points. What I'm going to argue is that this expected F norm can simply be compared to the F norm of these taus. That will be what I'll show in the end. And because the taus are roughly the expected LH maximum, so this will automatically follow. Okay, so that's the rough outline. So what's going to happen now? Now recall that this n greater than theta random variable is a sum of independent Bernoulli variables. I mean, so for the variable n greater than tau L, if the parameter is tau L, then I know that the sum of these probabilities is exactly L. So its mean is L. By Chernoff bounds, Chernoff concentration bounds, what I know is that if I take a random instantiation of the vector y, and I ask you how many coordinates are larger than tau L, that number has to be close to L. Okay, simply because of like strong concentration properties. This is like Chernoff bounds. So it cannot happen that so let me draw a random instantiation. Let's say I'll sample like a random thing. This, then so on. So I sample like a random vector from the distribution of y, and then look at this y down. So what I'm doing is the first coordinate of y, the largest coordinate, I'm putting it as a bar of length y sorted 1. And then the second bar is the length of the second largest coordinate in little y, and so on. So I stack them up. Now, because of concentration properties, the alpha Lth largest coordinate of y cannot exceed tau L with a large probability. It must be small, simply because of the mean of this random variable is L. So you cannot have more than alpha L many coordinates exceeding the threshold. If this were to happen, then you have actually witnessed a very rare event. Okay, so that's what is happening here. And simply by applying a union bound, what you can argue is that simultaneously for all L's going from 1 to n, the alpha Lth largest entry of y is bounded by tau L. So you can just do this by union bound, and you know that this happens with probability that approaches like 1 rapidly. So the gap is only like inverse exponential in alpha. Here alpha is some constant, say at least 10 or something like that. So for all alpha at least 10, this statement holds. And what you can show is, because f is a norm, the probability that this condition automatically implies that the f norm of y is bounded by alpha times the f norm of the tau vector. Stated other way, the f norm of this random vector y, for it to be larger than alpha times the f norm of the tau vector, these taus, tau 1, tau 2, so on up to tau n, the f norm of the random vector is very large, can only happen if one of these quantities exceeds tau L. Okay. So you basically do a calculation showing that if all of these events happen simultaneously, then the f norm must also be small. And so f norm being like very large means you have witnessed a very rare event. And you can just do like an integration calculation and show that the expected f norm of y can be bounded within a constant factor of the f norm of the tau vector. And because the tau vector is comparable to the expected Lth maximum vector, everything like goes through. I've skipped a few small details, but those can be like filled in if you're interested. So anyway, the theorem that we show is that the expected f norm of y can be compared to the, within like constant factors, is comparable to the f norm of the tau vector. There's tau 1, tau 2, tau 1. There's also like an additional term that I just like swept under the rug because I didn't want to like get into the details, but you can also do this. There is an additional term that's just needed for like to be recognized. It's important, but I won't be going into. Okay. Now, what's the second component in our framework? The second component is basically how to do stochastic top L optimization for a single L. Observe what are the challenges here. First of all, top L norms have a non-separable nature, which makes like controlling the expected top L norm very challenging. So let's say I asked you to control the expected LP norm or so. Like, okay, let me say it this way. So LP norm of X is simply the pth root of summation xi to the p. Okay, so you have this. And if you were to look at the pth power of the LP norm, then you have a separable form among the coordinates, right? So you know how much each coordinate is going to contribute to the norm, roughly speaking. Like that's what is happening. The LP norms are in some sense like more intuitive to view because of their separable nature. But top L norms, you don't know, like a coordinate contributes to the top L norm if and only if it's among the L largest coordinates, right? Otherwise, it doesn't contribute. So it depends on like what are those. And what people have shown, like in general, like in the past, when people have controlled the expected maximum, the top one norm of y, people usually do this by deriving some probability bounds on the coordinates taking a large value. So they control the upper tail of yi, and this implies like some bounds on the expected maximum coordinate of y. That's what people have done. But so this works for top one norm, but it's not clear how one would extend that for top L norms. So you have to work with like many more combinations. So here what we contribute is like we give like two simple proxy functions for controlling the expected top L norm of y. And these proxy functions, the nice thing is that like they have a separable form. They're easy to like view, and they only lose a constant factor, like a factor 2 and a factor 4. Like think of it that way. Like so they only lose like a small constant, and you can move away from these non-separable quantities to something that's separable. So what are these proxy functions? So the first proxy function comes from the okay. First of all, like I'm now interested in controlling this. I'm just interested, okay, how do I reason about the expected top L norm of a random vector? That's all. That's what I want to reason about. So the first one comes from trying to work with something called exceptional variables. So for a non-negative random variable z and the scalar threshold theta, I define the exceptional variable z exceeding theta as the following random variable. So anytime z takes a value at least theta, then I retain that value. And anytime it takes a value less than theta, I just round it down to 0. So this random variable either takes size 0 or it takes a large value. And that large value here is like at least some value, which is at least theta. So that's the exceptional variable. What we show is if you have a theta threshold, if you have a scalar theta such that L times theta is roughly the expected top L norm of y. Okay, so this is the quantity that you want to control. I'm saying if you have a theta which is roughly 1 over L times this quantity, then this separable sum is a constant factor proxy to this, the quantity that you wanted to control. Okay, so this statement does not hold for all theta. All it says is, assuming you have the right threshold, you can replace this expression with this expression. So what is this expression saying? It's simply the summation over all coordinates, the expected value of the exceptional variable that comes from that coordinate. The picture, I had to draw it. So let's say I have theta, and here I have probability that yi greater than theta. Okay. Now let's say I have some curve like this. Okay, just for a single coordinate, I'm looking at this. So what is this particular quantity looking like? I'm saying it's, so for some theta, it is basically this, going up to infinity. So the expected value of the exceptional variable yi with respect to the threshold theta is simply the area of the green region. Okay, look at the upper cumulative distribution function. Look at the threshold theta and like compute this area. That's what this quantity is saying. And what is this particular theorem saying? It's saying that if you have a bunch of coordinates and their own like bunch of regions. So this is for y1, and then y2, so on up to ym. Okay. If you have a bunch of these, and if the total sum of these areas is roughly the total sum of these areas is actually like roughly equal to the expected topple norm. And this is true as long as your theta is roughly 1 over L, the expected topple. So I won't explain like how this can be like actually used. You can look at papers or in the thesis, but the main idea here is that if you want to work with this complicated thing, it suffices to work with this more simpler expression. So that just depends on the individual coordinates. Okay. What is the second proxy function? This is like an even more simple proxy function. It takes some sort of a percentile viewpoint, like a fractile viewpoint. Recall that tau L was defined to be the smallest theta, such that sum of probabilities of a coordinate being large, that was like roughly L. What we show is that this expression, as long as you're in the vicinity of tau L, if theta, a scalar, is within the vicinity of tau L, then the expression L times theta plus the summation over all coordinates. I'm looking at the expected non-negative part of the coordinates. This one, this is roughly the expected topple norm of y. So this is actually like much simpler. Like, so I'm just like this is the probability that yi is greater than theta. This is theta. For theta equal to tau L, each coordinate like contributes something. Let's say this first coordinate contributes 0.2, some other coordinate contributes 0.3, and so on. You're just saying like, and then the expected value is simply this region. Now it doesn't have, so you don't have this region. It's just the region after that. So you can show that this expected calculation is basically this region. So as long as you sum across all of the coordinates and look at this portion, the area that lies beyond theta, that plus this L times theta expression, this is a constant factor. Okay, so that's the second proxy function. And okay, anyway, so these are like some two key contributions in this work, that first moving from arbitrary monotone symmetric norms to topple norms, and how do you control topple by working with some separable quantities. And with this, like we apply these to, I'll try to wrap up my talk in 10 minutes. And with this, like we apply this, these results, these tools to obtain an approximation algorithm for stochastic min-norm spanning trees. Recall that like we want to find a spanning tree T such that the expected F norm of its induced cost vector is minimized. The entries of this cost vector are simply the edge weights of the weights of the edges that participate in the tree. And recall the pictorial proof that like we related the expected F norm of Y to the F norm of the tau vector. There were some thresholds tau, some probability thresholds. So what we'll do is like for the spanning tree application, there is some hidden optimal cost vector W. I'm going to guess some TLs, which are roughly of the size of tau L of this random vector. And I'll do this for like L's that are powers of 2. And now what we do is like work each of these guesses leads to an LP. What I'm going to do is I'm going to write an LP which says I want to minimize this expression, this additive, this extra term. And then I'm going to say that Z should be in the spanning tree polytope. Here, like Z denotes whether the edge should participate in the tree or not. And then I'm also writing these tau L constraints. Yeah. Since TL is roughly tau L, you should have this constraint. It's the probability that an edge that is participating in the tree exceeds this threshold TL. This should be at most L. That's what like the definition of the tau L means. It's very easy to linearize this constraint. So you add these valid inequalities and you solve an LP. And what you can observe is that in this LP has a very special form. If you were to bring these L's, which are powers of 2, to the left-hand side, so you normalize the right-hand sides to 1. These are probabilities, and you have L's that are powers of 2. So for any fixed edge, if you look at the columns, the sum of the coefficients is at most a constant. So this is something called as like a bounded column sum property. Whenever you have this property, like for a matroid polytope, spanning tree polytope is a special case in matroid polytope. Then you can use an iterative, iterative rounding scheme to obtain a tree T such that roughly the tau L statistics of the algorithmic solution that you obtained is comparable to the tau L statistics of the optimal cost vector that you started with. Okay, so, and because the taus are comparable, the expected F norms are comparable. So that's the main idea for the spanning tree case. Anyway, our techniques for anyway. So the main.
Sorry, I have a question.
Yeah.
Like in the guessing, how do you ensure that it's like polynomial time? The guessing part of the.
Okay, good question. So what you can actually show is that if F were the sum norm. Okay, so if you're just looking at the expected sum of the edge weights that you pick in the spanning tree, it just reduces to the deterministic version. So for each edge, its weight is just the expected weight. Now solve the minimum spanning tree problem.
Okay.
So you get some number. What you can show is that all of these quantities are within a polynomial factor of this number. Okay, so what you do is like you basically have like a range. Let's say you want to guess these, say up to a factor 2. Okay, so what's happening is I know my right answer lies somewhere between 1 and m, say. So I'm only gonna guess up to factor 2. So I'll only guess like 1, 2, 4, 8, going up to like powers of 2. So I don't have to guess too many things. And also there is another important thing. I'm only guessing things that are monotone. So there are two things. First, I'm guessing like some log m many things, and I'm also guessing it for log m many coordinates. But what I know is that there is like a certain ordering amongst these. So you can actually show that the number of possible combinations that you can guess is polynomial in this case, like n is n. So say if you had to guess if you had to roughly guess log m many coordinates up to a factor 2 error, and you're promised that there is these coordinates are like either increasing or decreasing, then using just like polynomial in m many guesses, you can go up arbitrarily close to the hidden vector. Sorry, within a factor 2 of the hidden vector.
And don't you need like upper bounds or lower bounds on tau L of W?
Yes,
but I guess you have some. Okay, you might have some trivial ones.
You can actually show that like by solving the minimum spanning tree problem with expected edge weights, you can obtain some trivial bounds.
Okay.
I'm like slightly cheating here. Tau Ls can be arbitrarily spawned. But what we can also show is that if the tau L is very small, if some tau L is much smaller than tau 1 over m over n, then it just treat tau L as 0. It's okay. You can do that too, because it doesn't like cause much of a loss. So basically, like norms are kind of robust against small coordinates. If the large coordinates contribute a lot to the norm, and the small coordinates, even if you were to zero them out, it's okay. Like it doesn't matter much for a norm, as long as the large coordinates are compensating for it. So it's just some easy techniques. There's not much any deep math here. Any other questions?
Does this result extend to other matrices?
Yes. This approximation strategy extends to matroids, and so basically, like let me state our main result here. So we give a constant factor approximation for stochastic minimum norm, right? With arbitrary norms, monotone symmetric norms, and arbitrary non-negative edge weight distribution. Okay. For topple norms, we actually give a 2 plus epsilon. So here the constant is like 150 something, but here it's like only 2. And the same approximation strategy can be extended to stochastic min norm versions of matroid basis. You can do this for bounded degree spanning trees. You can do this for traveling salesman problem with some notion of how you define the problem. The same strategy essentially. For TSP, like I'll only like find a min norm spanning tree and then double the edges and do. Any other questions? Okay, now for load balancing, things are much more complicated. If you guys remember Rian talk from a month or 2 ago, he had to work with some effective sizes and all that, and things only get more complicated for general norms. I'll just state our results. So the reason load balancing is hard because your input consists of job sizes. So you're only told like this is the distribution for this job. But depending on which group of jobs you put on a machine, the machine load is in itself a complicated random variable. It is the sum of some random variables. And so as you can, like, it's very easy to see that the probability distribution of sum of random variables is some sort of a complicated convolution of the probability distribution functions of the components. So which is a very complicated quantity to work with. So load balancing results are like very technical, and in fact, like a bulk of my thesis is based on just like handling the load balancing case. So here, what are our main results? I'll separate like special cases and general case. I'll consider 2 kinds of generalizations. First is arbitrary job size distribution, and the other specialization would be when the job sizes are weighted Bernoullis. So the size of a job on a machine is either 0 or some size Sij, which happens with some probability Qij. So observe that this is like a strict generalization, the simplest generalization of the deterministic case, okay, to the stochastic world, the Bernoulli case. And I'll also have like 2 rows. One is for topple norms for a single topple, and one is for arbitrary monotones. So Topple norms and arbitrary job size distributions, we give a constant factor approximation. And this is a substantial generalization of Kleinberg, Rabbani, Tadeusz's work, and also Gupta et al.'s work, who gave an ordered one approximation for the top one case, for the L equal to 1 case. Kleinberg et al. Worked with the identical machine setting, and Gupta et al. Worked with the unrelated machine setting. Our results are incomparable to Molinaro's order 1 approximation for the LP norm case. Okay, because LP norms and top L norms give two different ways of interpolating between the max and some norms. So they're like kind of orthogonal. Okay, but our results like match the constant factor approximation guarantee of Molinaro. In fact, our results are like simpler and our constants are much better than Molinaro's. Next, so what happens when you have weighted Bernoulli job sizes and arbitrary monotone symmetric norms? We again give an order 1 approximation. And this strictly generalizes Chakraborty and Swamy's work, where they gave like a 4 approximation algorithm for the deterministic setting. Okay. Our constants are much larger. That's okay. It at least generalizes to the simplest stochastic setting. Okay. And for the most general setting, arbitrary job sizes, arbitrary norms, we give a order log n over log n. Okay, 2 logs here, 3 logs here, and n is the number of machines. This comes from using like a very powerful randomized rounding theorem. And I'm blanking out on who to credit this for, like you should know this, but it's cited in our in thesis. Yeah. But this is a theorem, like there is like a very powerful randomized rounding theorem for packing LPs. I think anyone who is interested in this field should just take a look. Many of the times, whatever problem you're working on might just fall into that framework for packing LPs. Yeah, anyway. Let me also just quickly mention what happens when you're trying to do stochastic min-norm optimization with Poisson random variables. Or let's like the way we worked with Bernoulli random variables. What if we work with Poisson random variables? So let's assume that we are in a stochastic min-norm instance where the entries of the cost vector are promised to be Poisson variables. Yeah. Where the probability distribution of a Poisson variable is given here. We use some property called as sure convexity. So what happens is like the objective functions that you're working with, when you try to control the expected F norm of the random vector, this one ends up being like sure convex function. It's a very nice structured function. By exploiting the sure convexity, what we show is that Poisson minimum norm optimization just reduces to deterministic minimum norm optimization, but with a different norm. So the norm that you started with here is different from the norm that you end up here, but you give a reduction. So this is actually another benefit of working at the generality of monotone symmetric norms, where because you have like because you have a very general algorithm that works for any monotone symmetric norm, you can solve like Poisson minimum norm optimization by reducing to the deterministic version with another monotone symmetric. So I think this is like a very nice benefit of working with monotone symmetric. Okay. Next, so just like concrete applications, Poisson minimum norm load balancing. The stochastic size of a job J on machine I is distributed as a Poisson variable with mean lambda ij. Observe that the load on a machine I is simply the Poisson variable with the parameter which is given by this. Look at the lambda ij's for all the jobs that are assigned to the machine I. Just add those means, and the machine load is also like sum of Poisson variables is another Poisson variable. So the machine load is also a Poisson variable. So things fall under this framework. What we show here is that we can obtain a essentially a two approximation for unrelated machines and a p-test for identical machines. Okay. And our result substantially generalizes Day, Khanna, Lee and Nick Page, p-test for the L infinity case. And if you are working with stochastic min-norm spanning trees with Poisson edge weights, then this can be solved exactly because the deterministic version can be solved exactly. I won't get into the details, but you can just solve the minimum spanning tree problem, minimum weight spanning tree problem, and that's it, optimal. Okay. With this, I'll like conclude my talk. Just state like all the main things that we saw today. We showed that the expected norm of a random vector is within a constant factor of the F norm of the expected sorted by vector. If you are ever staring at a quantity like this, maybe you should be staring at a quantity of this form. Okay, it's essentially the same of the constant factor losses. And then we gave a framework using this result. We gave a framework which says stochastic F norm optimization reduces to simultaneous stochastic Topple norm optimization with some budget, private budget for the Topple problem. We gave two constant factor proxy functions for controlling expected Topple. These proxy functions are separable, linear, and very simple to describe. And using our framework, we obtained approximation algorithms for stochastic min-norm, load balancing, and spanning tree problems. And some quick open questions. The most pressing open question that is left open from our work is there a constant factor approximation for stochastic min-norm load balancing when norms are arbitrary, like arbitrary monotone symmetric norms and arbitrary job size distribution? Like what we showed is log m or log m. Can we bring that down to a constant? This is open even in the setting where machines are identical. And then like another question would be just like how well can you upper bound expected F norm of Y in comparison to F norm of the expected sorted vector? Our current best bound is like 7.6. Right? We believe that it should be more like 2 or something. It's a very small, like these numbers are like essentially very close to each other. That's the belief, and observe that this has nothing to do with algorithms. It's just a purely mathematical question, an analysis question. What happens when you have the expectation and the norm? How much loss? And whatever, if you improve this constant, then it implies better constant for all the results that are based on our framework. And then you can also study stochastic min-norm optimization for other settings, like say bipartite matching, these are below. Yeah, with this, I'll end my talk. Thank you for your attention.
Do we have any questions?
So you say that the framework works as well for minimum bounded degree spanning trees, right?
Right.
Does the framework work as well if you have a minimum spanning tree problem and let's say a constant number of constraints? So like in the bounded degree spanning tree, you have, let's say, n constraints, one for each vertex. But let's say if you have an arbitrary constraints and let's say a constant number of constraints, like would the framework also work?
No, sorry, I'm a bit confused. Like, so can you state let's forget the stochastic version here. Like, just state it in the language of deterministic version.
Right. So like in the minimum bounded degree spanning tree, right, you have, well, for this problem you have the constraints that correspond to the spanning tree, but you have one constraint for each vertex. So like each vertex can have a degree at most a certain number.
Some prescribed, yeah.
You have n constraints, one for each vertex. So my question would be, let's say, you again are trying to work with a minimum spanning tree problem, but now instead of having the bounded degree constraints, you have arbitrary linear constraints. And let's say that
on the degrees,
it could be on the degrees or maybe on the codes or whatever. But let's say that the number of constraints are constant or something like
are constant. I think like, let's say what would happen if you had like constraints which say something like, it is saying summation over.
yeah, let's say you have constraints.
Yeah, you have something like alpha IV times some. I'm thinking like how the constraints look like. So this is this times maybe x times delta V or something like that. Is like the fractional degree times some coefficient alpha IV. This is bounded by some beta I, and I is like goes from 1 up to some constant C. Is this what you're asking?
Yeah, yeah. For instance, let's say something like this.
Okay. So what I would try doing is like I would look at like each like basically what we are trying to yeah, I would look at each edge and see like what is the column sum. In this case, the column sum is simply the sum of alpha IVs across these I's. So this is a constant, so I'm not too worried about this. And if the alphas are bounded, then iterative rounding just gives, say, a constant violation in these. So the rounding guarantee will be such that it will be like at most beta I plus some constant. And if that is something that is useful to you, then yeah, you get some algorithm which violates the constraints by small factors. Does that answer your question? Yeah.
Yes.
Thank you.
I have another question.
Okay.
Like norms, they have like a really nice notion of duality. Like, so for every norm, you have a dual norm. Does that like play any role on the things that you develop? Like, does that give you some nice insight about that?
Question. So let me okay, let me mention like a result from Chakravarti and Swamy's work. They actually use some sort of a duality argument to describe monotone symmetric norms. So for what they show is for any monotone. So I'm not gonna give like I don't really know how to answer your question as of now, but I'm gonna state a result. Maybe it tells you something. So given for any monotone symmetric norm F, fix one of these. There exists some collection C. There exists a collection C of non-negative vectors such that W and C is decreasing vectors, like non-increasing vectors, decreasing for all W and C. These are non-increasing, and then f of x is simply the supremum over W and C, W transpose this. So what is happening is monotone symmetric norms can be written as supremum over a collection of, so they are pointwise maximums of ordered norms. So what are ordered norms? Ordered norms are non-negative linear combinations of top L norms. Okay, so top K norms are easy to understand. They're just the sum of L largest entries. So consider non-negative linear combinations of top L norms. You get ordered norms. So W transpose X down hat, this can simply be seen as W1 minus W2 times top 1 of X plus W2 minus W3 times top 2 of X and so on. You can write like some expression like this. So you can view ordered norms as non-negative linear combinations of top and norms, and monotone symmetric norms are supremums of some collection of ordered. And this view of monotone symmetric norms is actually like it comes from these dot products that maximize the value. So basically, like you're maximizing the dot product between W and X, right? By sorting both W and X and decreasing order, you get this maximum. There is some like duality involved here, and this is like an interpretation. Yes.
If he finite,
I'm not entirely sure like if this gives you any new insights, but yeah.
No, that looks good. C can be infinite, right?
Yeah, C can be an uncountable infinite set. Yeah, uncountable set, yes.
Thank you.
Is there any hope to like generalize that matroid result to like matroid intersection?
Which one? Like, sorry.
Like you had like a result out for matroids, like optimization over matroids.
Oh, good question. Good question. Right. So the bipartite matching question is already.
Oh, that's still open.
Perfect matching is already in, right. That's still open. So
Right.
So bipartite, yeah. So the matroid intersection question is going to be a bit tricky. By the way, the bipartite perfect matching setting is open even in the deterministic setting. So forget like stochasticity. Just doing it in the deterministic case is not clear.
So like for any norm or like
yeah, so basically find a min norm, a deterministic min norm perfect matching. Yeah.
Okay.
And yeah, and also like if you're looking for another interesting problem, you can also consider these like the one I was stating, bounded degree spanning trees. Just consider the deterministic case and consider an arbitrary monotone symmetric norm. Okay. Now try to show some like, so if you recall like the bounded degree spanning tree case, the natural version where you're looking at the sum of costs of the edges that you pick in the spanning tree, and you want to satisfy the degree constraints, and the approximation result says I violate each of the degree constraints by at most one, and the solution I produce has total cost at most whatever is the total cost of the optimal solution that does not violate any of the degree bounds. So for the norm case, the degree violations are like a bit larger. It would be nice to show if, say, for general norms, you cannot come, say, within an additive one violation of the degrees or something like that. Like you have to lose something bigger. And usually in the stochastic world, like you lose like bigger constants, but it doesn't like, it's a more general question, but there are like some structural questions that we don't know for in the deterministic bounded degree spanning tree case with norm objective, because only the sum objective has been studied in some sense to near that the best possible result has been attained already. You violate degree constraints by, and you get like, you're within like 1x of the optimum. Yeah.
So to like, let's say for bipartite to get a result for any norm, it suffices to get a result for top L, right? By your reduction. Or does that not apply for the deterministic?
For top, no. So the thing is, if you're just working with a fixed top L norm, you can solve the problem optimally. So you basically like guess the Lth largest entry in an optimal solution, and you redefine the cost, saying the cost of an edge is either, if it's smaller than the threshold theta, then it's just 0. And if it is larger than theta, then you just look at the portion that is above theta. And you solve like a min weight perfect matching, min total weight perfect matching problem. You can actually show that like just for any fixed top L norm, you can solve the problem optimally. For ordered norms, which is like non-negative linear combinations of top L norms, you can solve the problem within constant factors. You can do that. So the problem begins from arbitrary monotone symmetric. That's where the.
But like, can't you use the yaw reduction for like arbitrary norms? Like,
but you have to simultaneously minimize all top L norms, right? So what happens is like, I'm giving you certain budgets and I want you to stay within those budgets for all L simultaneously. If you're only working with one top L norm, you can do. If you're working with an ordered norm, the reason you can do is, so if you have an ordered norm, you know what linear combination of top L norms it is. Okay, so it is okay to win in one of the top L norms and lose in say top 2L norm and so on. Like you can do like arbitrary linear combinations and your linear programming techniques extend with little work. But when you're working with a simultaneous supremum across multiple ordered norms, the only way we know of controlling this monotone symmetric norm is if I simultaneously control all of these at the same time. So it's just some technical details where arbitrary monotone symmetric norms are where like the challenge.
Yeah, thanks.
Any other question?
Let's thank Sharat.
Okay. Thank you.